recording. Oops, there it goes. Okay, so this particular one has a little bit more in the notes, especially some of the numbers. There's some stuff I'm going to show you how I calculated it, but I'm not going to ask you to have to repeat that. So yesterday I started talking about things called astronomical units, and because there is so much space, and no pun intended, there's so much space between stars and their planets, we don't measure them in miles and we don't measure them in kilometers. Now, just to put it in perspective, since you guys are used to miles, we're 93 million miles away from our star. But we like to use the metric system in science classes, so that translates to approximately 150 million kilometers. To keep this from being these big numbers with all these zeros, this is equal to 1 astronomical unit. That is how far we are from our star. Mars is 1.5. The oldest satellites that we have that are up, that are still functioning, are the farthest out. They launched in 1977. They're both about 150 astronomical units out. They've actually exited our heliosphere. They are interstellar. A light year, light second is on the next slide. I'm not there yet. A light year is the amount of length that light travels in 1 year, one of our years. Because like I said, we base everything off of Earth because we can. We invented all this stuff as far as the way that we comprehend it. Light does travel at 300,000 kilometers per second, or 300 million meters per second if you did it in the proper unit, but I'm not going to make you guys do a bunch of math. So in 1 second, light travels 186,000 miles in 1 second. And it takes 8 minutes and 27 seconds to get from the sun to us. So that should put it in perspective. I mean, we're tiny. I'm not saying that you are just, you're individually not, in the grand scheme of things, we're pretty insignificant, to be honest with you. I'm not trying to hurt your feelings, but it's true. We're tiny. 1 year is 9,460,800,000,000 kilometers is how far light travels in 1 year. Once again, we're 8.5 minutes from the sun. The first stellar system besides ours, the Centauri, the closest sun of that system is 4.2 light years away. That is how much of space is empty space. It just has little bits of matter that are thrown in intermittently. If we were 1 foot from the sun, then light would travel 120 miles in 1 year. If you shrunk it down to make it a little bit of a smaller number, just as a reference. Well, I'm going to show you how I calculated this. I'm not going to ask you to repeat that. You can type it down if you really want to. I don't know where I put my coffee. Let's grab one. And I do have paper versions right here if any of you were wanting a paper version. You want a paper version? The images, I printed off the images, but they're black and white, and you really need the color on them. Who else did want to keep? I may have to go make more copies. Like I said, I personally prefer paper. I think paper's faster than all this digital uploaded stuff. It's not as sanitary, okay? Like you said, you want one too? More.
I think pen and paper is the best way. So is it a point?
That's the assignment. Do you want the assignment as paper too, or are you going to do that online?
I'll do online.
You're going to do that online. It's actually easier for me to grade this. Did you want to do the assignment online, or are you going to do yours on paper? Wait. Is that everybody?
What assignment?
All right, so a light year. How I figured this out. I took, and I could have done this with kilometers per hour instead of miles per second. It's no big deal. But it travels 186,000 miles a second. There are 60 seconds in 1 minute. This is how you actually do chemistry math. But it's time conversion. It's not stoichiometry. There are 60 minutes in an hour. There's 24 hours in a day. This is actually not, this should be 365.24, but whatever. There's 365 days in a year. So I did 186,000 times 60 times 60 times 24 times 365. And this is how many miles light travels in 1 year. If I convert that to kilometers, that's where I get this number. 9.5 trillion kilometers. So light is extremely fast. It is the fastest thing that we are aware of. We keep saying that things can't travel faster than light, but when we talk about the Big Bang, they say in the beginning it was traveling faster than light. And I'll let a documentary go through that on Friday. Now, depending on what happens with my house, if it's even still standing, Monday I'm planning on reviewing, and Tuesday I'm planning for a test. I don't know. If this thing's a category 5, I'm gonna have to level my house. I don't know. I don't know. It's supposed to sell on Friday. This is so depressing. All right. Anyways, you don't have to write the long part. Yes, it's an extremely long distance. So we're going to switch over and talk a little bit about stars. Now, after this little intro unit, we're probably going to go into our specific system. We'll go over the planets. We'll go over our sun, specifically in depth. We will go over comets and asteroids, and things that are flying around. I'm trying to think if there's another one in there. Eventually, we will talk about black holes. We may come back and go a little bit more depth in the life cycle of stars. We're introducing it right now. But for now, there are a couple things that control the color and the temperature of a star. Its density, how much mass it is when it starts, when they blink into life and the protostar starts main sequence, that mass is a big factor on their temperature and their color. There are some stars that are smaller than Earth. Now, when I first started doing a space unit, oh gosh, like 8 years ago, the smallest known sun was a little bit smaller than Jupiter. Yes.
Are we taking notes on this?
You should have a link to it.
Okay, can I get a few paper copies?
Yeah.
That's not really. Stop it. Okay, why ask me when?
Oh, I didn't hear you then. I'm sorry. I apologize for seeing. But at the time, the smallest known star was called OGLE 122b. A lot of the stars are letters and numbers. They don't have Uncle names. And that one was just a little bit smaller than Jupiter. They are smaller than that now. We keep finding new information. This stuff does change. The largest known star for forever was called UY Canis Majoris. That's not true anymore. And you don't need to know any of these names yet. The largest in sheer size is called UY Scuti. The largest in mass, which is actually a smaller radius, is called R136A1. Now, like I said, that might change. It will change eventually. Now, generally, if a star is blue, it is young, it is large, and it is extremely hot. These are the hottest of the stars. This would be like Rigel. If it's red, I don't care how big it is. If it's red, whether it's a dwarf or a giant or somewhere in between, they're dying and they're cooler. And I'm going to teach you how to read this Russell diagram. You guys actually were sent a link to it that was a color version. It's really not that difficult. Oops. I'm going back. Yes.
What would we put underneath temp range and stars? Just that red to cooler blue?
Well, the coldest of the stars, and we tend to use Kelvin. You guys are familiar with Fahrenheit, which is why I put it in Fahrenheit on here. But the coldest of the stars do get a little bit less than this, but they start out at about 3,000 degrees Kelvin. Actually, they really go down to about 2,500 Kelvin, but oh well. And then they go up to around 30,000 Kelvin. And if they're red, they are cooler. In the middle is about where ours is, sort of a white to a yellowish color. And as they get up to blue, any shade of blue, then they're going to be the warmer ones. You ready? No, okay. No.
Weird. Blue's the hottest.
Mm-hmm. It has to do with the elements also that they are fusing. Blue stars, the younger stars, they're at the beginning of the fusion process, and they actually have more hydrogen than any other element. If they're in main sequence and they're a little bit smaller, then they're in the process of converting the hydrogen to helium. Once they run out of hydrogen, they freak out and they start combining the helium into carbon. They expand. The surface of the sun is further away from the core where the heat is generated. The surface is further away. It cools off and it shifts to red. Let's see what they say about this storm. So depressing. I moved up here to get away from those things. You ready now? Maybe. Let's see what my weather app says. Works. Go forward. Okay, now, we know a lot about stars because it's not like we can send a probe over there and collect some plasma and bring it back and analyze it. So we use various machines that use different parts of the electromagnetic spectrum, and it tells the information for us. The color, see what it says. And it's not telling me it's a category 5 yet. Last I heard it was 3.
It's category 4 right
Is
now.
it? Crap.
Oh,
I don't know, my house might still be there. So dependent on the color that's present, at least in this particular type, it tells us which elements that it is in the process of burning, or fusing is the right word, not burning. There are other spectrograms that instead of it using a color array like this, it looks like it's got peaks and valleys like an EKG kind of thing, and the peak is telling you what is prevalent. Those are more for taking a look at the composition and atmosphere of planets. So they have water signatures, they have ammonia signatures. But we use various scopes in space, and they take a look at what is evident, specifically which chemicals, which elements are prevalent. And no two stars are 100% alike. Now, if they're in main sequence, which is what ours is doing, they are in the process of taking their hydrogen and converting it into helium. That is the longest stage of any star's life. Anybody still need this one? No? Brightness. With stars, we call that luminosity. It means the same thing. If it's more luminous, it's a brighter star. If it is less luminous, it is a dimmer star. Now, this has something to do with how far away the star is from you. So we can talk about this in two different ways. If we talk about apparent magnitude, that is from what we see here on Earth. Now, if you have two stars that are equally bright, and one of them is twice as far away as the other, but they actually have the same luminosity, to our eyes, the one that's twice as far away will be a quarter of the brightness as the other one. I can show you the math how to do this, but I don't feel like doing it, and because I'm not going to ask you to do this on a test. Just like if you have a light source in a dark room, like a candle, you see like a halo of light around it on the table, and as you go further away, it gets dimmer and dimmer and dimmer. It's the exact same concept. That is apparent magnitude. The brighter stars are below 1. The dimmer stars are above 6. The reason why our sun looks so gosh darn bright is because we are so close to it. If you took all of the stars and put them in a line, all the same distance from Earth, specifically 32.6 light years away, they're all the same distance, Our sun would only be a 4.8, which is on the dimmer side. Where it is right now, we give it the value of 1 because we got to make this stuff up, and we like the number 1 a lot. So absolute would be if they are all the same distance, not where they really are, but all the same distance away from you. Apparent is where they are in their proper distance from Earth. It completely depends on your point of view. I'll need more time on this one. No? Okay. All right, so all stars in the beginning start as a stellar nebula. I don't care what they turn into. I don't care how quickly they form, how quickly they die. They all start off in a nursery called a stellar nebula. Okay, so matter has gravity, it's attracted, it starts clumping together. And before it's a true star, they go through a state called being a protostar. It's not really a star yet because it doesn't have nuclear fusion going on. They don't become a star until they're successfully changing hydrogen into helium in their core. Protostars don't do that yet. They're not hot enough to do it. They don't have enough pressure. They don't have enough density. There's not enough gravitational pull. It's just the early state. I can't remember if I put another slide on here or not. Let's see. I did. In the process of taking hydrogen and fusing their nuclei together to create helium, vast amounts of electromagnetic energy is produced. Within the core, all stars do this. They produce all types of the EM spectrum, not just visible light, X-rays, microwaves, radio waves. In fact, we will listen to our sun. The sun sounds like it has a heartbeat. We'll listen to a few of the planets. We'll listen to our moon. We will listen to the Earth. The Earth sort of sounds like an airplane. Sort of what it sounds like. But in the core is where all of this electromagnetic radiation is being produced. It gravitates from the core up through the convection center, and then it gets blasted out into space. We'll talk about that later when we talk about our sun. That's where we'll go into depth on that. So continuing on with protostars, because I couldn't fit it all on one slide. So we've got this clump of stuff that's getting denser and denser and denser. There comes a point, once it kicks on, that the gravitational pull that makes it want to collapse upon itself is completely counteracted once the bomb starts by the push out from the nuclear reaction in that core, and it becomes stable. This is called main sequence. It is officially a star, a productive star for that matter, when it does hit HR main sequence. They have to be at least 5 million degrees for this to occur. Somebody asked if the sun was on fire in one of my classes. No, it's not fire, it's plasma. It's a lot hotter than fire. So once again, this is the nuclear reaction, and it produces vast amount of the electromagnetic spectrum. We'll talk about that, I think more it's tomorrow. We'll talk about a few of the important telescopes. I'm not going to talk about all of them. There's too many. There's just too many. I need to add James Webb into the notes. We may talk about a few of the ones that just died. I might go back and add in Kepler and Cassini, even though they're dead. I need to go back and add in Juno. That's not in there yet. What's the matter? You don't know where we are at. We are. We are down here. Minimum temperature to begin the fusion of hydrogen is 5 million degrees. Second from the bottom. Oh, my attendance just logged out, or it's about to log out. All right. Down at the bottom, it is talking about main sequence. So I think it's on the bottom. I don't think it's on the back. And like I said, this is the bulk of any star. I don't care what size it is, how quickly it dies. This is the longest span of any star's life. It is successfully taking its hydrogen and it is beginning to convert it into helium. It is not going to hit the next stage of its life until all of that hydrogen is burned up. And now it's having to take helium and turning it into carbon. So main sequence, once again, you've got vast amount of radiation, which does not mean a bad thing always, it can be, that's being produced in the process of converting hydrogen into helium. Gravity is 100% counterbalanced with the outward push of that bomb.
Wait, vast amount of radiation that's being produced. Is that it?
For HR main sequence, it's the successful beginning of the conversion of hydrogen into helium. That is the longest part of any star's life. Each stage of the star's life cycle it's like a logarithm. It's a tenth of what the previous stage was. Our star doesn't go past carbon. In fact, most stars are average stars. That's the reason why we're carbon-based life forms, because most stars make carbon. All elements, well, all naturally occurring elements, they're made in stars. All right, so we're going to talk a couple of things that control the color. The original mass, when this thing changes from a protostar to a star, like a baby star, a true star, dependent on its size, can control its color. I mean, yes, what stage of life it is can control its color too, but this is the original color source. Your extremely large stars almost always start off as blue. Your normal size stars, those are going to be your white to orange range. We'll look at the analysis in just a second. And then your really little ones start off as red. In fact, the tiniest of stars are actually brown. We just discovered brown dwarfs not too terribly long ago. Now, these red giants and the supermassive and the ultramassive, the really big ones, so they take hydrogen, they've spent it all up. It's all converted to helium. And the star really freaks out because it doesn't want to stop the process. So then it's going to start taking the helium and it's going to go to the next element up, which is carbon. Now, oxygen is actually a mutation with this particular part. But once it starts making carbon, the sun expands in this process. And like I said, the surface of our sun will be past Mars at this point. It will consume Earth. And since the surface of the sun is so much further away from where the actual bomb is occurring in the core, the edges are cooler. And when the edges become cooler, the star shifts its color to red. That is why that happens. It doesn't matter the size of the star that does it. The edge or the surface, however you want to call that, is too far away from the core. It does not get enough of that energy from it. It cools off and it turns red. This thing's bothering me. particularly. Oh, I just explained this. The outside layer cools off, cooler temperatures changes the color to red. All right, this diagram, I'm going to explain how it works, and then we're going to take a look at it. It's really not that difficult to read. There are different versions of this guy. The one that I gave you shows a bunch of different stars as dots. And the bigger the star, the larger the dot. Those are your giants. They're up towards the top. The smaller the dot, the smaller the star. Not talking about brightness, it's just the size. In fact, the smallest of them are the dwarfs that are down on the bottom of the picture. Now, there are two measurements in these diagrams. Going up is luminosity. The higher up that star is located towards the top, the brighter it is. So then the lower the star is down towards the bottom, the dimmer it is. The sun, it's right there in the middle, it's right at 1. We give our star the value of 1 for a lot of things. Now going this direction, this has to do with temperature. And all the stars that are on this side are blue. And as you're going through main sequence, they start changing color. It goes through light blue to white, yellow, to orange, and then to red. So it does both the temperature of the star, it does the size of the star, and it's also going to do the luminosity. And once I show it to you, it makes a little bit more sense. Like I said, you have a colored version that I sent to you in Canvas. So this way is brightness, this way is temperature. And color. It actually puts the spectral analysis down on the bottom. That's the letters O, and then it goes down to M for the different class. You may have seen one of these when you guys did this in what, like 8th grade? You guys look at these diagrams when you were younger? You can remember? No? No? Okay. So hard. All right, so this is the diagram. You have this. These are all main sequence stars, okay? Your dwarves are down here. Your supergiants are up here. We have a little bit of an instability section here. And if you notice, to the left, they are blue. Doesn't matter if they're a giant or a dwarf. If they're over here on the left, they are blue. If they are over here on the right, they are red. The ones up on the top, this is Betelgeuse. This is Bellatrix. This is Deneb. These three are actually all in the constellation Orion. But these guys are your brighter stars. Here's the sun, right here. We have a value of 1. We base stuff off the brightness of our star. These would all be brighter stars. These would all be dimmer stars. And then if I go down, we're right in here as far as our class. And then you've got your colder ones over here. That's how you read that. Life cycle. I'm going to explain it to you, and then I'm going to go and I'm going to show you the second image that I gave you, because some of you, if it's done in like a picture, like a flow chart, this actually makes more sense. It's easier for you to learn. If it's a smaller star like our sun, an average star, it does its thing. It does main sequence for a very long time. It starts to burn up into carbon in red giants. Then it's going to collapse upon itself as a white dwarf, smaller than Earth. Our star will be smaller than the Earth once it is done. Now, there is a theory, given enough time, that even a white dwarf will not have the ability to produce light, and it will go dark. And that theory is called a black dwarf. We do not have any yet. The universe is simply not old enough to have any that have formed. But it is a theory, if you've ever heard that before. We just don't have any. Large stars. There are 2 types. I'm going to lump them together, and then I'm going to split them apart with the picture that I have. Large stars, these go past carbon. They go to iron. Iron kills stars. It is the death blow. Well, like I said, we'll get to some of this stuff later. I'll lump them together. If it is a massive star, it is from 1.4 to 3 times the mass of our sun. They do supernova. These are the ones that blow up. but they leave a bunch of neutrons behind. That's something called a neutron star, and they're actually really dangerous. If they're supermassive stars, they're more than 3 times the size of our sun. Those are the ones that make black holes. Now, y'all, we're learning a whole bunch of new stuff about black holes. These numbers may be changing. In fact, they probably will change as we learn more information. So I just said the elements are made in stars, but iron kills them. So all of the heavier elements that are above iron, the bigger elements above iron, those are generated with supernovas. That's where the heavy metals come from, things like gold, silver, platinum, palladium, all of those. They actually are caused by these supernovas. And then they get spread out throughout the rest of the universe. Then they coalesce. And if we're lucky, you have enough stuff that coalesces and another Earth pops into existence around its star. But all of the elements that make up those planets, they came from a dying star before. They just get recycled. I mean, the hydrogen in the water that you drink, the H2O, it's the regular water, that could have passed through a dinosaur's digestive tract. I mean, everything gets recycled. I mean, the whole saying, you are what you eat, that's a true statement. That's where your body gets the stuff in order to repair itself. So if you don't eat very well, you don't take care of yourself, your body doesn't age as well. Or if you do other bad things to yourself, don't do bad things to yourself. Your body will take that and incorporate it as part of itself. Oh, there's Overton. I need to ask him about your test. We need to do that, actually. I just saw him walk by. It's Roker, right?
Yep.
All right. So this image you have. Yeah.
What happened? What happened?
Then I'll just do that. I'll just do that for it, and then I don't have to worry about it.
Sounds good.
Awesome, thank you. So this is, you have this. I sent this to you. You start off as a nebula. Average stars will red giant. When they shrink back to a white dwarf, they leave behind a planetary nebula. Yes, they may become a black dwarf. Both of your massives will supergiant. They will blow up. Your massives will neutron star, and your supermassives will black hole. Honestly, some of you actually learn from stuff like this better than you do just a list. We do have a little bit left, just in passing constellations, because I know we're running out of time. In the northern hemisphere are circumpolar, around the North Pole. That's what that means. There are certain constellations that are always up. This is true in the southern hemisphere, but it's around the southern pole. They have a different set of constellations than we do. You do not need to know these by name yet. You will come back and do a constellation unit. They're always there. The Big Dipper and Little Dipper are always there, and Draco snakes in between them. Once again, they are circumpolar. They are always up. Now, the other constellations that you may have heard of, those are the zodiac constellations. You weren't ready? Okay. The different month that your sign is for is that constellation that's at the ecliptic. You should know what your zodiac sign is.
I'm Virgo.
I am a Capricorn. Most of the constellations do not look like they are named for, but we will take a look at the zodiacs and some of the other major constellations. I don't know if I'm gonna do it the next unit or not. I'll figure it out. Did you get it? You got it. All right, so the zodiacs, they are on the ecliptic. That means different times of the year have different constellations that are primarily up. It is January, February, March, April, May, June, July, August, September, October, November, and Sagittarius is around December. Yes, you do actually need to know the day because some signs there's some people that are right on the cusp. The last little thing that you guys have, blue stars are younger and hotter. I mean, I've talked about it, but red stars are older and cooler. That's the last little bit. And then the last thing that you guys have, you have this also. This chart, because I'm not about to make you write every single bit of this down. I gave it to you as reference. Blue is O class. It is the hottest, specifically ionized helium. If you want to know specifically the element that causes the color, that is what this chart does. We're pretty much right here. The really old ones are making the heavy metals and they are dying. So let me freeze this. Let me double check my remotes because I heard a couple beeps. Yes, a couple beeps. Where's my attendance? Well, poop. What did I do with my attendance? There it is. You do have one on galaxies if you did not do it yesterday. The one that's today's is up there. They're only 10 questions long. I'm not trying to make this class difficult, but they are assignments. If you haven't done them, you need to go back and do them. Okay, this is, okay, she's already in. She is in next class. Cole, did I get you? I did get you. HR main sequence is the longest part of any star's life cycle. It is when it is changing hydrogen into helium. That is main sequence. Okay, I am going to stop presenting. I'm going to wait for that to come back to me.
Yeah, and he's saying it's really, really bad. Show me a video.
Yeah.
It's
Port Arthur's a lot further south.
Got picked up and thrown into the street. And it hasn't even hit yet. It's just the wind and the rain. Shut up, Alex. Shut up.
Okay, so I did not see this one.
What's happening with the test?
He said you had 100. So I'm just gonna, I'm not gonna pull stuff over. I'm just gonna import the grades for you. Thank you, you too. All right, so we had this child, this child, this child, this child, and this child. Oops, I went too far. Yes.
I have a couple questions.
Yes. Now let me get the right slide up for them. And I need to make a couple more sections of notes. Freeze. Set first.
Hey, girls.
I need to make more copies of my notes. Yes.
I have a question on the most of the stars are in the page, right?
No. not. The leaves are actually in the
They're
pillow.
the disc.
They're in the disc. I'm gonna go make a couple more copies of this notes, just in case any of you want a paper copy. This is my last one. Right back. Yeah, most of the stars are located in the disc. Anybody want to take a copy of the notes? You don't want to type. You actually can access the 50 notes. You access the Google Slides and you can use the reference. Otherwise, just taking down the spectral shot and take you forever. Yeah, actually, I'm going to do that here in a second. Anybody else want a paper copy? I'm going to take a look. Even though this is actually a rather populated class, I did get to you guys. So, because it should not take me this long to take attendance, but I don't have one that looks like the way that you're sitting until now. So, we are in 7th period. Oh, I spelled her name wrong. I spelled her name wrong. Jayden. Let's off the A. So we got Dean. I don't see Jaden though. She's not here. Okay. Okay. So I've got Dean and Chris and Josh, then Jonathan, and then why don't I have you written? What's your last name? Westbrook. Oh, you moved from over there or something, didn't you? No? Yes? Okay. Let me just shift you. Okay. So Madison are now next to each other. Great. Okay. Megan. Fernando's not here. Where?
Bernie has moved.
You moved. You want to move in the back. Are you bad? No, where did Ty go? Okay, so but that means that we can't have you and Ty in the same seat. So I'm gonna move
Ty where Bernie was.
Move Ty where he was in 10. All right, so all right, and then you are now 16. All All right, so I have to do this because I don't know if this hurricane is going to be a category 5. I think it is a category 4 already. It is whipping into my house. There is a good chance that I am going to have to do damage control. I don't know when I'm going to have to go down, but it's 6.5 hours each way.
You have a house?
I have a house that is supposed to sell on Friday. It is supposed to close on Friday. And it has a hurricane that's a category 4. The eye in Orange, Texas. It's where the eye is going to come ashore. So like it's probably going to hit somewhere between Port Arthur and like Cameron, which is in Louisiana. And Orange is the last town before you hit Louisiana. I literally am 7 miles from the Louisiana border, just north of 10. We're in trouble. I'm almost hoping that it's leveled. Almost. Because, well, I mean, I have flood insurance. I have windstorm. You have to because you're in hurricane territory down there. But yeah, it was supposed to sell on Friday. It's my luck. I haven't slept in like 3 days, so I'm tired. All right, so we got, and then Leah. And now who's behind Leah? That is, what is your last name? What is it? Nick Anderson. Okay, I did not have your number down on here. That's why. Nick. All right, so then we have Chloe and Brady and Jonathan, Fernando, and then you go by Ryan, okay, and Nathaniel and Aiden. Did I miss anybody? Who's in the back? That is back there. Okay, so, but you need to sit back there, or are you charging your stuff or something? Yeah, okay. All right, I think that's everybody. And this way, if I do have to have a sub, your names are where you are sitting. Okay, I got more people that came online. This one logged in. This one logged in. Courtney Lowry, okay, that is a remote, so that's logged in. And Carla, where are you at? Okay, so, when you go into Canvas, and I'm hoping that, well, I need to present the right slide here for them. Share, present, okay, and unfreeze. I'm hoping I can get through this quick enough where I can go through and let you know. Now, I know, like, Courtney, you're new. I went back and I got rid of the deadline dates for a lot of things because, y'all, there is a lot of you that have not been either uploading or turning in stuff. Okay, some of you do still need to do the safety test, especially those of you that are listening remote. You can go back in. You only get 1 attempt with the safety test. I've changed it so these quizzes, I actually will give you a second attempt if you make like, a 30 on it, because these are actually graded assignments, these little 10-question assessments from what we talk about. There was one yesterday on galaxies, and today we're going to talk a little bit more about measurements in space, and then we're going to talk about stars in general. Tomorrow we're going to talk about telescopes. I need to add a bunch of stuff to my notes because they're not up to date. James Webb isn't even on that one. Had a friend that lent me some stuff, and I greatly appreciate it, but it's not up to date, so I got to fix it. The opener. This is an opinion thing. You may not even know that there are different types of stars out there. Our sun is an average sun. That is a good thing. They last a long time. The Earth is in what is called the Goldilocks zone. It is in the habitable zone from our sun. Now, let's think. Now, the Earth would still have to be in the Goldilocks zone, but let's say instead of having a normal sized sun like ours, we put a supermassive star there instead. Now, obviously, the Earth would have to adjust where it was, or it would like be consumed by the surface of that star. So let's pretend it gets shifted out. So it's still in the habitable zone. What do you think it would do to life? How do you think it would have to adapt? If you've got a supermassive star, no matter what color it is, what would it do? Y'all, the bigger things are, the bigger the gravitational pull is that they exert.
Everything would have to be in the water.
Well, I mean, it's like I say, it's sort of an opinion. I do go back and I read what you guys put as your opener. There are work 10 points.
The planet would have to be further away.
It definitely would have to be further away. Yes. Like I said, it would have to be in wherever that respective livable zone would be. All right, so I'm gonna go forward. You actually have a little bit more on these notes as far as numbers are concerned. I will actually show you how we calculate how far light travels in 1 year. I'm not going to ask you to duplicate that. We're not going to do a lot of math in this class, but we measure distances in space by the distance that we are from our sun. We call that an astronomical unit. And the distance between us and our sun is 1 AU. Well, this is awesome, but you don't know what that represents. 1 AU is worth 93 million miles. And we don't use the standard British system in science. We use metric. So that translates to approximately 150 million kilometers away. I've mentioned this a couple times. It takes 8.5 minutes for light to travel that 93 million miles. It's quick, but we're really far away. Now, we use AUs to measure distances between stars and their planets. Mars is 1.5 AUs from the sun. The furthest satellites that we have in space, the 2 Voyagers that were lobbed up in '77, they're 150 astronomical units away. They are interstellar. They have punched out of the heliosphere. It's the farthest that we've sent anything from Earth. I don't know how much longer they're going to keep going. They will eventually run out of their nuclear fuel and they'll die. But they're still alive, sending us back data. So I'm going to show you how I get this number. I'm going to show you the actual number, even though it's not 100% accurate. It's close enough for what we're going to do. If light travels at 186 miles a second, that means in 1 second, it travels 186,000 miles in 1 second. If I multiply, because you should know that there's 60 seconds in a minute, and there's 60 minutes in an hour, and there's 24 hours in a day. I have that on the next slide. You do not need to write that down unless you really want to. When I multiply that all out and get it up to a year, it's 9,460,800,000,000 kilometers is how far light travels in 1 year. 1 Earth year. If I made this a little bit smaller, let's pretend if this is the sun, we are 1 foot away. Just say that 1 foot represents the 93 million miles. This trillion number, if we're 1 foot away, light travels 120 miles in a year. So that is how much of space, and no pun intended, that's how much of space is empty space. Why it's called space. All right, so how I did that. You don't have to write the conversion factor that I used, but I always get people that like, where the heck did you get that number from? This is how you calculate it. I went ahead and changed it from miles per second first, and I got this number, and then I used the conversion factor to go between miles and kilometers, and that gave me that 9.5 trillion kilometers in length. But that's not a light second. That's how far a light year is. If I knew how far around the Earth was in kilometers, I could tell you how many times the light would go around the Earth in a year, but I don't remember the actual. I don't remember that value. I have to look it up. Oh, please don't let my house flood. Don't let a tree go through my roof. It took almost 2 years for me to completely remodel after Harvey. So depressing. Does anybody still need this? When I get to these pictures, I sent you a Google slide that has these on it. You have access to these and they are in color. I did print them off, but black and white doesn't really show you very much. Uh-huh. More than welcome to. And if you want to keep a hard binder, you're more than welcome to. It is convenient that Canvas will grade stuff for me, but it won't export it into the school's grade book, so. All right, don't worry about writing. That is a long way. That is an extremely long distance for it to travel. We're going to start talking about stars. Now, we're going to come back and talk about our sun in the next unit. Talk about our planets, talk about our natural satellites. We'll talk about our sun, how it works. We'll talk about asteroids, comets. I'm not sure if I'm going to push the constellations in there, if I'm going to try to keep your tests nice, small chunks. I said, I sort of get to do what I want. It's really nice. But there are a couple things that control the color of stars. And they're not all like ours. They all look, I know our sun actually looks a little yellow, but I'll explain what the chromosphere is later. Some stars are super small. When I first built my space notes, I don't know, a decade ago, the smallest known star was OGLE 122b. It was slightly smaller than Jupiter. A lot of stars have numbers and letters. Some of them have cool names, some of them don't. That's not true anymore. I do not know the name of the brown dwarf that is the one that's smaller than Earth, but some stars are extremely tiny, and the smallest of the small are brown dwarfs. The largest stars are huge.
The smallest ones live the longest?
Yeah, in general, the smaller they are, the slower they burn through their fuel.
But they all have the same fuel?
They all start off with hydrogen. Only the really big ones make the heavier elements because you have to have a lot more pressure to get up to iron. The smaller stars won't go past carbon. We'll get to that. And you're just sort of jumping ahead a little bit. The really big stars, the largest one used to be UY Canis Majoris. You don't need to know these names yet. We'll talk about it later. That's not true anymore. To my knowledge, the largest star in sheer size is UY Scuti. The largest star in density, in mass, is not the same star. That's one R36A1. That may change too. It probably will as we have better telescopes up and we find more things. Color. The cooler the star, the closer it is to death, and the redder it's going to be. I will explain this when we talk about supergiants in just a couple slides. The younger the star, the hotter the star is going to shift the color to blue. These are in the process of making carbon. These are in the early stages of their fusion, and they're converting hydrogen into helium, but the bulk of this star is hydrogen. I will show you how to read that chart in just a bit. Which, if you took a space class in like 8th grade, you may have seen some of these diagrams before. I doubt it, but you may have. Are you ready? I think that is a yes. All right, these colors. All stars are unique as far as their composition. Now, there are some stars that have things in common with other stars. So main sequence stars are all doing the same process. They may not be the same temperature. They may not be the same percentages of hydrogen and helium, but they're in the beginning stage of their life. So we have machines that are in space that detect chemical signatures and can turn it into a color spectrogram like this. Sometimes, like the old school ones I remember from college, when we put the chemicals in the glass plates and we ran them through the machine, it would spit out this printout and you would see all these like peaks and valleys, and I actually would tell you the specific chemicals that were present in that sample. Little slightly different when you're talking about looking at things from far away and you don't actually have the chemical inside it. But some of these spectrographs look for things like water. When you talk about the ones that look at planets, sometimes they look for ammonia. Sometimes they look for amino acids. They're looking to see if there are building blocks for life that are present. It's not saying they see life. Are there things there that are present that would be indicative of life? And the Kepler telescope was one of those, but I'm almost positive that it has gone black. But all stars are different. Okay, brightness. I'm going to take a look at a Russell diagram. I'm going to show you how to read it. They're not hard. Russell diagrams have luminosity on one side. Luminosity is the word that we use for how bright it is. The more luminous it is, the brighter it is. The less luminous it is, the dimmer it is. It does depend on how big the star is, and it does depend on its temperature. Magnitude. There are two ways you can talk about this. Apparent is the way we see it from Earth. Okay, so if I have two stars and they are equally luminous in relationship to each other, they both have a luminosity of 2, okay? But one of them is twice as far away as the other one. The one that's twice as far away to our eyes would look only a quarter of this one's brilliance, because how far away they are from what we see affects how much brightness we see. Just like if you have a candle in a dark room, you know how you see the halo of light around it, and as you go further away, you don't see as much of light on the table? It is the exact same concept, it's just it's traveling through space. So apparent magnitude is how we see it from here, and the smaller the number, the brighter it is, the larger the number, the dimmer it is. Absolute magnitude is different. Absolute magnitude would be if you could take all of the stars and move them all exactly 32.6 light years away from us and look at them all like they're lined up in a row. It's perspective, it's point of view. To put it in perspective, our sun, if it was lined up on it and we could look at it from Earth, it would only have a magnitude of 4.8. Its magnitude from here is considered a 1. We'd like to give our sun the value of 1 a lot. Now, it just depends on how it's talking. Parent magnitude is from here. The other magnitude is if they were all the same distance from us. You ready? Okay. How stars begin? They all begin as a stellar nebula. That is the nursery of stars. I will show you a picture representation of this for those of you that like to look at it as an image. You learn that way better. I provided that with you with that supplementary material. In a nebula, I think there's one more on here. Yes, okay. In a nebula, you have gas. You have cosmic gas. And matter is attracted to matter, so they start clumping up. And eventually you get enough clumped up where it starts creating large amounts of pressure on those things that are in the center. And before the star actually kicks on, it's called a protostar. Fusion doesn't happen yet in a protostar. It's about to. It just hasn't clicked on yet. Mostly because it hasn't gotten hot enough. You haven't had enough pressure, enough gravitational pull. So a protostar is not doing this. This is the nuclear reaction that starts all suns or stars, however you want to call them. It takes 2 different hydrogens and it smashes them into the next element and it makes helium. Once this starts, the star has born and it is no longer a protostar. This protostar has to reach at least 5 million degrees before this will start. It's a lot. It's a lot. In this process, massive amounts of energy is released. It's done so in the form of electromagnetic radiation. So everything from the light that we see to X-rays, to microwaves, to radio waves. And because the sun emits radio waves, we will listen to it. Sounds like it has a heartbeat. It's really weird. In fact, we'll listen to lots of planets. We'll listen to Jupiter and Saturn. They're really weird. We'll listen to our moon. We'll even listen to the Earth. So this is the actual process that changes it from a protostar to a star. I think I've got one more thing on protostars on the next slide. The temperature is on that one too. And then we're going to start talking about main sequence. I hope I am not muted. I would have hoped that they would have told me. I think I told you I did that in my second period the other day. On my present, oh, I'm sorry if I was echoing. I turned the presentation volume off. Where's my thing? All right. Okay, so once again, so we're still sort of talking about protostar. We haven't kicked on the bomb yet. So once you have enough gravitational pull, you have enough pressure, you have specifically enough temperature, and that's caused by the pressure of everything trying to shove everything all in one spot. Your nuclear reaction occurs, and now we're creating what is called main sequence. Main sequence, which is I think the bottom thing on the front of that paper if you're writing it out, or the bottom thing on the first page, is the changing from hydrogen to helium in the core of a star. Yes, it has to be at least 5 million degrees to get this chain reaction to start. In the process, massive amounts of energy are produced. I was always taught, and honestly, I think when I was your age, it's because the teachers didn't know any better. But I was always taught that we wouldn't be able to do fusion on Earth, that it would like blow up the planet, pretty much. Fusion happens in the stars. Fission happens in our nuclear power plants. Well, that's not true anymore because we have things called tokamak reactors. They almost look like giant metallic donuts, and they are creating the interior of a star inside these generators. We are trying to change the way that we are doing travel through space. They're just not, they can't sustain themselves for long yet. But there's a few of them. I know the Chinese have one, the Russians have one, the Swedes have one. I don't know where ours is located. They're all over the place. It's actually pretty cool stuff. It's terrifying at the same time, too. Okay, so your main sequence, if you didn't get what I just said, because it was the bottom one that was on there, that is when the gravitational pull in has kick-started the bomb, which is pushing back just as hard, so the star is not collapsing. It's also not exploding. It is stable. That is main sequence. That is the longest part of any star's life. Our star is doing it right now. It's been doing it for about 4 billion years. It's going to do it for about another 4 billion years before it runs out of hydrogen and it starts converting that helium to carbon. And then it's going to swell past Mars, and it's going to be dust. And then it's going to collapse back upon itself, and it's going to be smaller than the Earth. It's going to be a softly shining diamond for the rest of its life in the form of a white dwarf. Literally, a chunk of carbon, a chunk of shining carbon. There's a reason why life is carbon-based on this planet. Most stars are average. If they die, they turn into giant balls of carbon. They get eaten up by black holes. They end up spitting stuff back out, and that spreads all the elements across the rest of this universe. But you're made in stars. It just so happened to coalesce here in this little corner of the Milky Way on this rock that we call Earth. And somehow everything happens, so the things that make up you are what makes up you. All right, so the original mass of the star also determines color. There's a couple things that determine color. When they are first born, the very big ones are blue. The biggest of the stars are blue at birth. One of these days, I'm going to learn that that's going to happen. Leave. Okay. The average medium-sized stars, they tend to be yellow and white, which is where ours fits in. The really, really little ones are red. The extremely small ones are actually brown. That's a newer discovery, are these brown dwarfs. They're the smallest ones that we know of. Your giants. I had somebody, they were like, I don't understand why blue is hot and red is cold. I don't know why it wouldn't be the other way around. It's the way that it works. Your giants, ours will be a giant, just a giant. Your massive stars are going to be your super giants. There's also ultra giants out there too. I don't talk about that in here. But when this is gone, the star freaks out and it's going to start burning its helium and it's going to fuse it to carbon. And in this process, the star expands astronomically out in 3 dimensions. The surface of our sun will be past Mars. It expands that kind of level. And now the surface is so far from the core, it is much cooler. The radiant energy, it sort of dissipates as it's trying to travel through the interior of that star. That's what causes the giants, the red ones, not the blue ones, not the purple ones, but the red ones. That is what actually makes them cooler. That is what shifts their color to red. And this is where our star stops. Our star can't go any further. In order to go further than carbon, you have to be bigger, you have to have more pressure. And those will go to iron before they blow up. Our star will not blow up. It will eat us, but it will not blow up. Okay. I just explained this. You should, I've said this a few times. The surface expands, it moves further away, it cools off, it turns red. Okay, diagrams. I'm going to explain it and I'm going to show you how to use it. The one that you have, I sent you a second link. This one, that's nice and colored, the first one. The stars are represented by dots. The dot is representative of its size. The bigger the dot, the bigger the star. And the ones on the left are blue. They shift color to white, to yellow, to orange, and the ones on the right are red. So the hotter stars are on the left. The cooler stars are on the right. There's numbers going up the left-hand side, up the y-axis. That is brightness. The further up it is, the brighter the star is. So the further down, the dimmer the star is. The further to the left, the hotter the temperature. The further to the right, the cooler the temperature. And then there's a bunch of letters that are down on the bottom. It starts with an O and it has a few more and then it ends with an M. The very last slide that you guys have as reference explains what the spectral type is, what that letter means. So up the side is brightness. The sun is at a 1, as we say so. And across the bottom, you are decreasing in temperature. That is the way that this diagram is put together. The 2 scientists that invented it were Hertzsprung and Russell, which is why it's called a Hertzsprung-Russell diagram. They named it after themselves. We're going to take a look at it. You have this. You have this. As long as you have a Chromebook, I sent you a link to it. Here we are. We have a brightness of 1. Told you it was a 1. We get to do what we want with our sun. Hotter on the left, brighter at the top. So we are smack dab in the center because we base everything off us. We're sort of like the neutral star, if you will. Your dwarves are down on the bottom. This is your spectral type. We'll come back and talk about that in a bit. Your supergiants are all up here. Some of them are hot and some of them are cold. This is Betelgeuse. In fact, this one, and this one are all in Orion. I don't know where all of the stars are. I'm going to have to go back and brush up on my constellations so I can make sure I teach it to you right. This is the second image that I gave you for those of you that looking at the picture helps you learn. I understand some of you like to learn that way. I provided it for you. It's like a flow chart. Average, all stars start off as a nebula. Average stars will giant, will contract, leave behind a planetary nebula, and then there will be a white dwarf for the rest of their life. The theory does go that eventually they will run out of light and the light will not be there, and that's a black dwarf, but we don't have any yet. The universe is not old enough. And then this one puts the massives together, but the picture splits them apart. So stellar nebula, you've got your massive and your supermassive. They're both massives, they're both big ones. And both of the massives will supergiant and they will supernova. But the massives, which are the smaller of the two, will create a neutron star made of neutrons. And then the supermassives are the ones that make black holes. They're lumped together here. So I just said the stars stop making elements of iron. So where do all the heavier elements come from? It happens in here. It happens with the death of the star when it explodes. And you get things like gold and silver, platinum, palladium, not the man-made elements, but the natural ones. They're all born in that supernova. So neutron stars are from massives. Black holes are from supermassives. That's it. Do you have a picture that does this for you? I'm about to show it to you. Y'all done with this one? Yes. Okay. This is the image that you have. Some of you just like to learn from this. That's the exact same thing that was on there, but birth, averages, giant, shrink to make a planetary nebula. We know for sure they make white dwarfs, but we hypothesize that they will eventually turn into black dwarfs. We just don't have any of them yet. Your massives and your supermassives, obviously this is main sequence here. They're going to supergiant. They're going to explode, but the massives, which are up to 3 times the size of our sun, will neutron star. The supermassives, which are more than 3 times the mass of our sun, those are the ones that black hole, but they still blow up. The little ones like ours, they don't blow up. A little bit on constellations. We will come back and do these later. I'm not going to fit them all in here. Yes, I don't want to give you too much information on a test. I don't think that that's fair. We are in the northern hemisphere. We have a North Pole. The star's name is Polaris. It's right here. There are certain constellations that are always in the sky going around the North Pole. They are circumpolar. They go in a circle around the North Pole. Constellations. You do not need to know their names yet, but that is the Big Dipper, the Little Dipper. That's the Dragon, Draco. It's these guys. They're always up. Well, I mean, it's got to be dark out. Yeah, okay. But they're always up at night as long as you don't have clouds in the way. The type of constellation that you're probably actually familiar with are the zodiac constellations. And we will take a look at all of them. You hopefully know what your zodiac sign is. So you have a constellation that corresponds to it. Now, the zodiac, because they're what's called on the ecliptic, they're only up at certain times of the year. So we've got January, February, March, April, May, June, July, August, September, October, November, and December. Now, there are certain dates. I remember like 5 years ago, they were talking about putting a 13th constellation in there, and it was like messing up everybody's dates. So I'm going old school because I really don't want to learn a 13th constellation. But if you're Gemini, it's the twins. If you're Taurus, it's the bull. Aries is the ram. Capricorn is the goat, fish, ugly mermaid thing. Scorpio's the scorpion. Libra's the scale. Leo's the lion. Cancer's the crab. I can't remember what Sagittarius is. What is Sagittarius? I don't know. I have to go back and look at it. But these are the ones that you're going to see at specific times of the year. Y'all, the southern hemisphere has different stars than we do. They have a southern pole. They have different constellations than we see.
It's a bow and arrow.
It's a bow and arrow. Thank you. Yes, I have to go back and look. Let's see. You have this also. Okay, these were the letters that were down across the bottom of that Russell diagram. The hotter stars are blue. This is why. This is the element that's causing that. And then we start changing colors. The Earth is right around here. And then your coldest of the stars that are getting ready to die, they are making your heavier metals. And eventually they blow up. If they're big enough stars, they blow up. The last two things that you guys have down on the bottom, because I have other Russell diagrams, but it's the same thing as you had before. This one just doesn't have the stars on it. It's the same thing. This is the same thing. It's just done as a spectric analysis. It's still the same thing. This is another one. I mean, it's the same thing. It's just, I like the one that has the little stars on it better. The last two things that you have, blue stars are younger and burn hotter. Red stars are older and burn folder. That's the last two that are at the bottom. I'm going to freeze this. I'm going to go to my meet, lock this. I told you I was going to let you know. And this is mostly, I think, for my remote. I have people that are missing the safety test. Now, you have a little bit of time. It's just a 10-question assessment. Yes, it is a grade. Yes. Sure thing. If you did not do the one on galaxies, I went back and I changed it. So you actually get 2 attempts on these assignments. If you really do bad, you can go back and try it again and it'll take your higher score. I do have some people that need to go back and add in the syllabus. In fact, I'm looking at it right now, and I got one from Misty if you are online. Safety test, off on the side. Caleb, if you can hear me, you need to go back and take it. Natalie, you need to go back and take it. There is no score. If you had not been doing the openers, you need to go back and do them. This will not export the grades to the grade book from Canvas, so I have to manually pull them out. Yes. It is, you weren't here yesterday. As long as you have access, you can go to yesterday. It was about galaxies. So it'll say 825 opener. Let me go into Canvas and I can tell you specifically what I called it. And what I did down at the bottom in the section, it says 825 notes. What I do is I record myself in 6th period and I upload it to YouTube. And then I embed it into Canvas because I don't put my PowerPoints on the thing. In fact, the only way people get my notes is if they have a modification that they need. Some people need a paper copy of notes or whatever. And I'm still going through all of those. In fact, let me look and see if I can upload my YouTube. ESS live stream, but that was from yesterday. You know what? I'm still recording. I recorded 2 classes in a row.